Welcome students. Today's video lecture is about the liquid drop model of a nucleus. So I prepared a small presentation on this. Let's go ahead. So what is the liquid drop model of a nucleus? It's a theoretical model to explain the various experimentally observed properties of atomic nuclei. So we have been talking about the different properties of a nucleus like the size, the shape, the observed magnetic moment, the observed nuclear spin, the binding energy, etc. All these can be experimentally measured. Now, thing is, can we have theoretical models of the nucleus which can explain these experimentally observed properties? So, different models were proposed, and the liquid drop model was one, which was first proposed by Niels Bohr and Wheeler in the year 1937, and of course independently by Frankel. So this is a model of a nucleus, which is a theoretical model which tries to explain the various experimentally observed properties of a nucleus or of atomic nuclei. So in this model of a nucleus, an atomic nucleus is considered to be analogous to a liquid drop. So here we are saying it is analogous to a liquid drop. We are not saying it is same. It is similar to a liquid drop. So why do we consider an atomic nucleus to be similar to a liquid drop or analogous to a liquid drop? This is based on the following similarities between a nucleus and a liquid drop. So these similarities can be put down as below. So first, this may seem trivial, but both the atomic nucleus and a liquid drop are spherical in shape. So invariably they are spherical in shape. Of course, for larger liquid drops, for example, if the size of the liquid drop it increases, the spherical shape is a bit distorted for a liquid drop, because if we imagine a liquid drop which is very big, because of gravitational effects maybe, the shape will be distorted. Similarly, heavy nuclei with more number of nucleons, that is larger mass numbers, they are found to have some distortions from the spherical shape. Again, like a liquid drop, the density of nuclear matter is always constant. For example, let us consider the common liquid that we talk of, water. At a particular temperature, the density of water is always constant. Even if we take a glass of water, a bucket of water, or a tank full of water, the density of water, temperature remaining the same, it is constant. Similarly, the density of nuclear matter is always constant. So these are two figures. This is a liquid drop. An ant is trying to see what it is. So similar is, this is a figurative, what to say, depiction of a nucleus having the protons and the neutrons. The protons and the neutrons, that is the nucleons, they are held together in a closely packed structure, and the structure apparently is spherical. So these are just comparisons between a liquid drop and a nucleus. What are the other similarities? Surface effects. A nucleus has a surface barrier analogous to the surface tension in a liquid. So this is a depiction of a water droplet. So here we can see the surface tension of water. Why does it arise? It arises because the molecules at the center of the liquid drop, they are attracted or they are pulled in all directions because of the intermolecular forces. But a molecule at the surface, near about the surface of the water drop, it has a resultant force inwards. So this gives rise to a tension on the surface of water. So this model you can easily compare with the nuclear model in which the nucleons inside the nucleus, at the core of the nucleus, they will be interacting with nucleons, 12 other nucleons in the closed spec structure in all directions. However, the nucleons residing at the surface, they will experience a resultant force inwards. So similar as in the case of the liquid drop, in a nucleus also, there is a surface tension. We call it the surface effect. There is a surface barrier. So this is another similarity between a liquid drop and a nucleus. Also, the surface effects are responsible for the spherical shapes of the liquid drop as also the nuclei. So the nucleons, or hence the liquid drop molecules at the surface, they are pulled inwards in all directions. As a result, because of the surface effect, the liquid drop attains a spherical shape. Same will be the case with that of an atomic nucleus. Like a liquid drop, a nucleus also cannot be compressed. It is incompressible. Liquid drop as also a nucleus. The intermolecular forces as also nucleon-nucleon forces are short-ranged. In a liquid drop, the molecules, they interact only with the nearest neighbors. They are attracted to the nearest neighbors because of the intermolecular forces. Same as in the case of the nucleons. The nucleons, they interact with other nucleons by the strong nuclear force. Now this strong nuclear force is short ranged, so a nucleon will interact only with its nearest neighbors. So that is another similarity. The next, evaporation in a liquid drop is analogous to the phenomenon of radioactivity. Evaporation. If I have, this is evaporation from the surface of a lake. So even if we consider a single liquid drop, if we leave the liquid drop to itself, suppose we keep a drop of liquid on a surface, leave it like that and come back after a few hours or the next day. So what you will see is that the liquid drop disappears. What happens? The drop, it evaporates. Without any external influence, the liquid drop evaporates. Same is the case of radioactivity. If I have a radioactive sample, substance, or an amount of a radioactive substance, this radioactive substance will keep on emitting particles and radiation spontaneously. You don't need to do anything from outside. This is a nuclear phenomenon. So a radioactive nucleus, not talking about the substance as such, even if we have a radioactive nucleus, it will emit particles and radiations because of the phenomenon of radioactivity. So the process of evaporation can be compared to the phenomenon of radioactivity exhibited by radioactive nuclei. Another similarity, fission in a heavy nuclei is analogous to breaking up of a large liquid drop. So if I have a heavy nucleus like that of uranium, a neutron with sufficient energy, it comes and bombards this heavy nucleus. What happens? This breaks up into two parts of comparable masses. This is important. It breaks up into two parts of comparable masses with the liberation of large amount of energy. Or in other words, a heavy nucleus breaks up into two parts of comparable masses. Similarly, if you see a liquid drop, these days it's raining. So if you see the drops hanging in a bar, you will see that as the rain falls, the drop, it keeps on increasing its size. Beyond a limit, what happens? The liquid drop, it breaks up into two parts. One part goes down, the other part it remains. So other way around, if I take a big liquid drop and disturb the liquid drop, what will happen? It will break up into two parts. So this breaking up of a liquid drop can be compared to the process of fission exhibited by heavier nuclei. Also, the process of fusion of lighter nuclei is analogous to condensation of liquid drops. Fusion, of course, it's not that simple. We need very high energies. So deuterium and tritium, they will fuse together to form helium with the liberation of large amount of energy. So basically, we are interested in the process of two lighter nuclei coming together to form a heavier nucleus. Similarly, condensation of liquid drop is an analogous process. Smaller liquid drops, if we bring it together, it will come together to form a larger liquid drop. So these two processes of fusion and condensation are comparable to one another. This is another similarity between a liquid drop and a nucleus. So based on these analogies, so what was thought is that as because the nucleus and a liquid drop, they have these similarities, in the liquid drop model of a nucleus, it was proposed that an atomic nucleus is analogous to a liquid drop, and in this model it is considered that a nucleus is a spherical entity in which the nucleons are held together by the strong nuclear forces. These are the considerations of the liquid drum model of a nucleus. The radius of the nucleus is proportional to a to the power 1 by 3, where a is the mass number of the nucleus, that is, the total number of protons and neutrons in the nucleus. So the radius of the nucleus, that is the radius of the spherical nucleus, is proportional to a to the power 1 by 3. The nucleons in the nucleus behaves collectively. In this model of the nucleus, we don't consider the nucleons inside the nucleus to behave independently. We consider that all of them, they behave collectively. So the nucleus is a collective unit consisting of all the nucleons. And the nucleons inside the nucleus are in continuous motion and they undergo frequent collisions with one another. However, the surface forces prevents the nucleus from breaking up. So what are the successes and failures of this model? The liquid drop model was successful in explaining the observed bulk properties of the nucleus. For example, it could explain the variation of binding energy at large, or it could explain the binding energy of nuclei, different nuclei, how it arises and how it varies with mass number. It could explain the phenomenon of nuclear fission. The liquid drop model was successful in explaining this. It could explain the phenomenon of nuclear fission. Sorry, one is fission, the other should have been fusion. It could explain the phenomenon of nuclear fission, and it could explain the phenomenon of nuclear fusion, not fission, sorry. Also, it could explain the phenomenon of radioactivity. However, it failed in explaining the exceptional stability of nuclei at particular number of nucleons. For example, if we see the binding energy curve, that is the variation of binding energy per nucleon with mass number, we see that for lesser mass numbers, till about A is equal to 20, certain peaks are observed in the binding energy curve for mass numbers corresponding to 4, 8, 12, etc. The liquid drop model could not explain this. It could not explain the erratic variation of binding energy per nucleon for lesser mass numbers. So this can be explained with another model called the shell model we'll be talking about later. Also, it could not explain the experimentally measured values of nuclear spin and nuclear magnetic moment of different nuclei. So, what it basically means is that the liquid drop model was successful in explaining some experimentally observed properties, but it failed to explain some other properties. So this model, you can't say it is a complete model. So that is all about the liquid drop model of a nucleus. So as because it could not explain all the observed properties, other models were proposed in which the nucleons were treated independently. So that one model is the shell model of the nucleus we'll be talking about in the next lecture. Thank you.